at surfaces. And one of the things that we quickly concluded was that in the case of a surface which is sort of defined analogously to a curve, meaning that it is treated as a mapping from parametric space. For the surface, it happens to be a unit square, and the expression of the surface or the representation of the surface maps the UV values to a point in space which lies on the surface. And in some sense, the representation for the equivalent surface representations for the curve types that we studied for the curves, right? The parametric cubic curve, right here, the Bezier, and then somewhere below we will get the spline. Very similar, where it is now defined by basis functions in both u and v in the two directions. And you have again different degrees in the two directions, because that is, in the case of the Bezier, it is controlled by the number of points, and you can have different points in the u direction and v direction. And the grid of points that you define constitutes the control polyhedron. Now, instead of a polygon, it's a 3D entity, and it forms a control polyhedron. And an example is shown here, right? And so the main point that we concluded was that the representation for surface is not a big deal at all, right? And in fact, this is the slide where we concluded that my surface is seen as a curve of curves. So it can be seen as a locus of U curves whose control points change with V, or it can be seen as a series of V curves whose control point changes with U, right? And therefore this representation, and now here you have the spline representation, will represent a surface, right? A parametric surface. And so representation is sort of done, right? But the problem with this representation is that you will have to specify these control points, right? Which are now no longer in an array, but a grid, right? Which means that on a 2D screen, it's very hard for the user to input these points on the grid, right? Even if you assume that each of the U curves in this case is on a plane, right? You still will have to move out of plane to look at the other next U curve that you want to define and so forth, right? Control polygon that you want to define. And therefore, it becomes a very cumbersome exercise to define the control points. And so we go back to this distinction of storage and definition. Remember, we had said in the case of AI and the geometry coefficients BI, right? Which was nothing but the two endpoints and the tangents at the two endpoints. Okay? These are intuitive for the user to define. These are very unintuitive for the user to define. This is the representation. This is the definition, right? Now, the same way, we also have control points, PIJs, for both the Bezier and the spline. Now, that in 2D, no, I shouldn't say 2D, 1 degree of freedom, PI is not too bad. Users can define an array of control points. But for a surface in 2D, it's very hard to define a grid of points. And therefore, we focus more on the construction and not so much the storage, right? So the user is interested in how to construct or define the surface to the system, and the system will take that definition and build a representation which is like your spline or the Bezier curve. So one of the first that we saw was a ruled surface, which is a special type of a surface, where the formal definition is that, I have 1 second, I'll just defer this. Yeah, so you have the two curves, which are QU and P of U. They are given. And when I say the curves are given as input, means I have a representation for that in a spline or the Bezier form. And the ruled surface is defined as the locus of straight lines that join points on the two curves, right, for the same value, corresponding values of u. So u0 on one curve is joined to u equal to 0 on the other curve, and so it goes till u equals 1 at the end of the curve. So you have two examples. And then I just quickly illustrated how you can write down the representation of the surface given the input that the user has given, namely these two curves, right? P of u and Q of u are given, and we can, based on that, write down the expression for the surface, right? The only unknowns are the degree in V, because it's a line, we can fix that to be 1. And the minimum number of points that we can get away with is 2, and therefore I know my number of control points, and the control points are just matching points on both the curves, right? So while you don't define these representation, you only define these two curves and say I want a ruled surface, the system is able to construct an exact ruled surface. The next one that we were looking at was the surface of revolution. Here again, the input from the user is a curve that is to be revolved. And when I say again curve, which means that you have a representation for that in your favorite form. In this case here, we have shown a spline and the axis about which it has to be revolved. And sometimes the angle with which you revolve as well. Sometimes you don't want the full surface of revolution. You may stop it at some angle. And so you might input that angle also as part of your input, right? So again, the same claim, which is that from this input, the representation of the curve, which is right here, and the axis, we can write down the representation for the full surface, right? We saw how the value of M and L are determined. L is 3 because the curve in the V direction, because it's a surface of revolution, will always be a circle, right? Or an arc of a circle. And therefore it's quadratic, and therefore L is 3. Now, if it's a full circle, we know how many control points we need in that. We have just done this. Of course, this is not a unique result. You can have any result. And depending on the angle that you want the revolution to be done over, right? You can have any the right number of control points. So if you want a half circle, or if you want only a quadrant, then the number of control points automatically get adjusted. Okay. So the only thing left here is to determine the control points, right? And the control points actually is also not too difficult. So let me just draw the control polygon, a fictitious control polygon for this curve that has been given to us, right? Let's say this is the control polygon. Okay. So I have 1, 2, 3, 4, 5 points. So this is P4, C4 rather, and that's C0. And the way you find the other control points, Pij, right, is as follows, that Pi0 equals Pi8 for the case of the full circle is nothing but Ci. So let's say I is equal to 3, then my first and the last control point for the circle is this, and the remaining points are found by taking a square that passes through this point and is perpendicular to this axis. Okay. Actually, this line, this point should have been here. Bad drawing. Let me see if I can improve it. Okay. So I take this point and an edge and draw a square orthogonal to the axis, right, centered at the axis. and passing through this C3. So that's my first and the last point. The remaining points are PI1, PI2, PI3, PI4, PI5, PI6. So this is P36, P37, and P38. Okay, and you do this for all the control points. So here again, you find a square which is orthogonal to the axis and passes through this point C0. That gives you the remaining control points. Right? And so you are guaranteed to get an exact solution. Okay. So you only have to give the axis and the arc, and then you get an exact solution for the surface of revolution. Keep in mind that most systems would not allow. So supposing if you have your curve is that, they will not allow the curve to touch the axis. Right? Some may do this, but by and large, you typically don't allow the endpoints of the arc to touch the axis. That's one. And the second, of course, is that you have to define the curve and the axis in the same plane. Otherwise, it's not going to work. So you can't have a situation where the curve is here and the axis is like that. That is not allowed. Right? The system will not be able to handle that. Okay. So that's the surface of revolution. And the next category is what we call as a sweep surface. Right? Now, most of you are already probably familiar with this. There are two inputs that the user needs to give. Right? One is known as a profile curve. In this case, the circle, right, which is being swept in this path, is the profile curve. And the path along which it is swept is called the path or the guide curve. Okay. And so there are two possibilities that happen. One, let's say that, what did I do? So let's say this is my path curve and this is my profile curve. Right? Now, one sweep could be where, the circle doesn't change the orientation at all. It stays like this everywhere. That, as you know, is rather ugly looking, swept surface, right? But what typically you would want in a sweep surface is that the cross section or the profile curve stays perpendicular to the path all the time. Okay. Now, as it happens, in this case, you can get an exact solution. Okay. You can write down an exact representation for a swept surface where the profile curve does not change its orientation with respect to the path curve. But as I said, the requirement by and large would be where the profile curve is to be maintained orthogonal to the path curve. Then for this, unfortunately, you do not get an exact solution. You can at best get an approximate solution. Right. So we will see how this solution is obtained. But just before that, I just wanted to mention one more point, which is that, if the path curve was a straight line, then you can imagine you get a right circular cylinder, right? And that's you can get the exact solution for the right circular cylinder. Now there are tools, CAD tools, which allow another piece of input in the case of the sweep curve or the sweep operator, sorry, where you can insist or give another curve. In this case, let me just draw a line, right? And sort of insist that the curve, profile curve, always stays in contact with this line, right? So, and is centered on this axis. So what will happen then is that you will have a scaled, Unfortunately, my drawing is bad, so I'll just make it a little larger. So you will get something that looks like a frustum of a cone. Okay, so that's also possible in the case of a sweep, regular sweep surface. But the general sweep, as I said, there is no exact solution. So how does it work? The way the system will respond to your request for a general sweep, because obviously you have been creating these kind of sweep surfaces in CAD systems, so it is possible, right? The way it works is that you create multiple instances of this cross section or this profile curve at various locations in the orientation that is desired, namely orthogonal to the tangent locally. Right? So you have these many curves now, 1, 2, 3, 4, 5, 6, 7, 8, 9 curves are there. And you go back to the original problem that we had posed, that now I have 9 curves that I know lie on my surface, find the surface. Okay, so that's the problem we had started with earlier also. And so we come back to finding a solution to that problem, which is given a bunch of curves that have to lie on the surface, find the expression for the surface. Right? You may recall that we said that this operation is called lofting. And so this is the manifestation we saw earlier, right? That I have these cross sections and I want to fit a surface through those cross sections. I have some aerofoil sections along this and I want to fit a surface that contains all these aerofoil sections. A simpler example, I have 3 curves and I need a surface that goes through those 3 curves. Okay. So this is something that is to be solved now. And as I said, the general sweep problem also reduces to a lofting problem. Because there again, you are given a bunch of curves along the path, right? And you want to be able to fit a surface that contains these curves. So how do we find this? I just want to take a minute to walk you through the process. As I said, the idea or the intent is to give you a feel for what is happening in the lofting process. But you know, the tool, of course, you don't need to have this knowledge to use the tool to create lofted surfaces, which is the objective in this class, right? So what is going to happen if I state this mathematically? Let's say if I'm given these curves CR, right? R is equal to 0 to capital R, right? So I have R plus 1 curves. So CR of U, right? So if this is the U direction, is equal to okay. Sorry. What did I do? Did I do this right? No. No. Sorry. 1 second. So NIK VR. What have I done? All this expression is saying is that for specific values of V, right? So my U direction in the, my U direction in this curve is along here and the V direction is like this. So this is the U direction, right? And this is the V direction. So what this expression is saying is that at select values of V, right? V0 to VR, if I evaluate the surface, I will get a curve in the U direction, and that curve must be exactly this curve. Okay, So how do we solve this problem? The way we solve this problem is what we did earlier, right? That I rewrite my surface, right, in a slightly different way. Right, that's my surface. And this, for these values of VR, must be equal to CR of U. And what is CR of U? I know that expression, I equals 0 to N, some Ci Nik of U. Right? So what does that mean? That means that the CIs, which are my control points of the input curves, right, are points on the V curves. So what are the knowns here? This is known, right? This is known. This is known. I need to guess at L and M, then I can solve this problem. We have seen this. This is nothing but the curve interpolation problem, right? Now, before I illustrate this, I just want to remind you of one thing, which is we said that if R, the number of points given, right? So Ci j here, C1j, C2j, C3j, Crj, if that is equal to M, then you know that we get an exact solution to this problem. So which means that the PIs I get will, if I plug it back into the surface, these curves will exactly lie on the surface. And that's what we want. We don't care too much about what happens in between, right? There may be some deviations from the swept surface in this case, or your lofted surface in this case. But as long as these curves are exactly on the surface, you have met your goal, and therefore this process allows you to do that. So I don't know how many of you remember what we did in the last class. I'm just going to flash that same slide again, right here. So in the last class, right, we said that I'm given the PIJs, which are these, dots, the gray dots that are on the surface, right? So I can take individual rows of those input control points and determine curves in the U direction, right? And if I pick, evaluate that curve, right, pick a point on that curve and find control points all over, then I draw a curve through those control points defined by those control points. I'll get a point on the surface. Right? That's the explanation. So now the order does not matter, we said, and therefore, if I were to define, right, a series of V curves given the control points, right, I get these red V curves, and I evaluate the curves at a fixed value of V at the blue dots, right? I get N points. I use them as control points and I get a U curve, right? And that gives me a curve that lies on the surface. Now this is, you're given the control points and you work to find the point on the surface or the curve on the surface. In the lofting or the sweep case, you're given this curve on the surface. Just like this blue curve, you're given multiple such blue curves. So their control points are given to you, right? The blue dots are given to you. So all we are saying is that you take corresponding, a blue dot, say for example, for I is equal to 0 here, and take all the blue control points here for R such curves and fit a curve through that, right? That control points of that curve will be a column of your control polygon. So that's what this is saying. right? So if I solve this problem, I'll get the jth column, ith column, sorry. Okay, so I'll get pi 0 to pi capital small m, and that's nothing but the ith column of my control point. So this control polygon column I'll get. Next, if I do it for the next value, I'll get this, and then I get this, and so here, sorry, I do it for this first, then I do this for this, then for this, and then for this, and I will get each time these points. Okay, and how do I get those points? They are fitting a curve here, right? And this curve in turn, we have the how do I fit this curve? By finding points on that curve, right? And those are the control points of my U curve. So if I have multiple U curves like that, so these control points are available with me, the blue dots, right? So I know this curve and I know these control points. So I pick, say for j equals m, I pick this for the next input curve, the previous one and the previous one, and I get those points on the curve, and I find the control polygon of a curve that fits through those points, and that's my control polygon. Okay, so that's why, and because the numbers are small, I can choose r to be equal to m, and therefore I will always get an exact solution. So while we said that for the sweep surface you will not get an exact solution, the closest we get is that these section curves that you have generated to define the surface, they will lie exactly on the surface. Okay, so that's the guarantee you get, that those curves will lie exactly on the surface. So also with the lofting case, the input curves that you give, they will lie exactly on the surface. Okay, so you can see some examples here, right? You have circle, and the sizes keep changing, and you get a lofted curve through those surfaces. Okay, so these are the broad ways that you construct surfaces in CAD systems, right? Typically sweep and lofting are the ones that are used the most. Surface of revolution, where it is required, then you can use the surface of revolution where you get the exact solution. Okay. Now, before we move on to the next problem in surfaces, I just want to talk a little bit more about this continuity. We have been talking about it a little bit, but not formally defined it. So what I want to do now is put down a definition for this, because we will need this as we go further down with surfaces and solids. Right. So there are, remember I had said this, that C denotes continuity, and the number on the superscript denotes the order of continuity. Right. C0 means you have point continuity, meaning that I don't have a break in my curve. It's watertight. Right. But it doesn't mean that, so I can have, this can be a C0 curve. Right. There is no break, and that's a C0 curve. C1 continuous means that it is continuous up to the first derivative. Okay, and so that's the C1 continuity. So which means that in the same surface, if I leave it like that, then the tangent is continuous everywhere, and that's C1 continuity. And you can keep going further down. C2 is continuity in the second derivative, right, which sort of relates to curvature. And this is usually important for rendering tasks, that you would not want the curve to have discontinuous in the curvature. Then the rendered image doesn't end up looking good. We will come back to this point again when we talk about quality of surfaces. But right now, I want you to appreciate that this is continuity. And when we talk of the curve or surface derivative, right, which means tangent and magnitude, we imply that this is parametric continuity. Okay. Now, in CAD, we define another type of continuity. Where did that go? I thought I had a slide. Oops. Okay, there's a mistake. I'm missing a slide here. But anyway, let me write it down here. And when I post it on the site, I will fix this. We have another type of continuity called geometric continuity. Okay, where the same definitions apply, except that we only expect the directions to be the same, not magnitude. Okay, so that example is here, for example, that if I have two curves, right, which are having a junction at this dark dot that we have put here, right, if the derivative happens to be, having a magnitude at this point so much in this direction, then another curve, right, a red curve, which has, black curve, which has the same direction of the derivative at that point, the first derivative at that point, but its magnitude happens to be small, is termed to be G1 continuous. Okay, and the same argument applies for C2 and G2 and so forth, where here both direction and magnitude are same. Here only the direction is same, magnitude can be allowed to float. Okay, and clearly you appreciate that in a lot of instances it's very difficult to maintain continuity in both magnitude and direction. So geometric continuity enables designers to sort of tweak points, control points, etc., so that the direction is the same. They don't worry too much about the magnitude. Okay, so this is an important distinction that you should keep in mind about geometric and this. And so some examples here, point discontinuity, point continuity, then there is tangent discontinuity, and there is tangent continuity, and here you have curvatures, right? So, I mean, you can look at two examples here. In one case, you have a very smooth variation in your curvature. Okay, so it starts at some value, dips to some value, crosses over, there's a point of inflection, and it reaches a max, and then again starts dropping, crosses zero again, and then comes the other way. Then you have other kinds of surfaces where the curvature variation looks like this, right? The surface or the curve may look smooth visually, but the variation actually is quite erratic. And this is what we will cover when we talk about the quality of curves or surfaces. Okay, so while this is continuous and therefore smooth, right, as you can see from the picture here, right, but it is not a good surface from a point of view of rendering because of these variations in the curvature. They are smooth variations, but they are variations nevertheless. Okay, so that is something that needs to be understood. So we will talk about this at the end when we talk about quality of surfaces, how to evaluate quality of surface that you create. Okay, fine. So we are now ready to start last topic in surfaces. As I said, surfaces will get over fast primarily because we are not so much interested in the representation. It just comes for free from the curves. It is only the construction techniques that we need to know about. Right? The last problem that we need to look at for surfaces is an important problem, which is known as the surface intersection problem. Okay, now on paper you may think that this is an algebraic problem. Why are we worried about it? But as it turns out that for the CAD systems all across the board, right, this is the weak link in almost all CAD systems, right? And my intent is to tell you why in today's class and give you some example in the next class. Okay, so illustrate it in the next class. So what is the problem? Algebraically, here is the statement. And I don't want you to worry too much about it except to note what the algebraic issues are, right? So let's say I have two surfaces, S1 as a function of the two parametric variables UV, S2 as a function of two parametric variables TW, and I want to solve this equation. Now, algebraically, what is the structure of this? How many unknowns are there? Can anyone tell me?
Two.
Two. Which ones?
U
Okay.
and T.
But what about V and W?
Uh,
Why are they not unknowns? If you look at your surface, right? Remember what did we say? We said that you need to fix both U and V to get a point on the surface.
yes.
Correct. So you cannot use only one to fix the point. You can fix one by getting only a curve then. If I fix V, I get a curve. If I fix U, I get a curve. But on that curve where my point is, I need to fix the other variable as well. And therefore, as you can see now, you have 4 unknowns. Correct? Now from these 4 unknowns, how many equations do you have here?
Two.
If it is 2, yes. When will you have 2 equations? What is the condition?
Both sides.
Huh?
One for the S1 and one for the S2.
No. I want them to be equal, no? For all values of U and V, I want to find points which lie on both the surfaces. That's my intersection, right?
So one doubt. So are the two surfaces having different control points? So merging them.
Yes. Do I have an example of a surface somewhere over here? Okay, here. So imagine, right? If I were to take this surface, this looks very similar to this, but let me say that I put this surface, right, on top of this and ask you to find the intersection of these two surfaces. Okay, or the wing. Let's say you have the wing, you shove the wing through this, right through the middle. So I have one surface here, and let's say, the parametric profile of this ugly looking wing, but anyway, I hope you see the point, right? So this is UV, and this is TW. Okay. Now a simpler one where you can relate to this is, let's say, this surface here and a plane, right? That's a simpler example. Again, you have two surfaces, 1 and 2, and you are finding the curve of intersection. Okay. So it's just like you find the intersection of lines, right? How do you find the intersection of two lines? I have one line which is A plus TB and another line which is C plus UD, right? So I have two unknowns, T and U, and I have how many equations? These are all vectors, right, in space. So I have 3 equations. I have AX, BX, CX, DX, AY, BY, CY, DY, AZ, BZ, CZ, DZ, right? So 3 equations, 2 unknowns. And here, in this problem, I have 3 equations and 4 unknowns, right? 1 equation for the X coordinate, 1 for the Y coordinate, 1 for the Z coordinate, right? Because that's the mapping, right? U and V map to X, Y, Z in space. And therefore, I have the structure of this equation is I have 3 scalar equations in X, Y, and Z, but 4 unknowns in each of them, U, V, T, W. So clearly you have a problem, right? You cannot solve it. Or rather, the only way you can solve it is by fixing one of the variables arbitrarily, which means that the result that you are going to get from this intersection has 1 degree of freedom. And what has 1 degree of freedom? What entity? Point, curve, surface. Which one has 1 degree of freedom? Take a guess.
Curve.
Curve, exactly. So that is what is telling you that structure there, that I have 3 equations and 4 unknowns. That is telling you that I am expecting my result to be a curve. Okay, because the only way you can solve this is by arbitrarily fixing any one of them and solving for the rest. Because once you fix one of the unknowns, then I have 3 equations and 3 unknowns and I can solve that. And then you repeat it for all values of that other variable that you fixed. But since you don't know which one to fix, you may as well do it for all of them. That's how the structure works. And I will just tell you that. But the main conclusion now from this discussion is that the result that you are expecting is a curve. Is it a curve or many curves? Think of a corrugated sheet and a plane. What are the results of the intersection? I'll get one curve here, I'll get one curve there, one curve there, one curve there, one curve there, one curve there. So that's my first solution. Right? So when I want to solve the intersection problem, I would like to get the curves of intersection. What are the other possibilities? Are there any other solutions possible? When two surfaces intersect, can anything else happen? Or can you expect any other result?
Lofting.
Yes, go ahead.
The lofting.
What about lofting?
The edges of two curves kind of having a similar to lofting. Yes, a wild guess.
I'm not able to understand that, but yeah. But my question is this, that, I hope you are convinced now that the result of the intersection of two surfaces will be either a single curve or many curves, right? Yes. I'm asking you now that are there any other possibilities for us to consider? Well, there is one possibility, right? What happens in this case? What is the result in this case? No intersection, null set, right? Fine, yes. So that's one solution. Any other? Any other you can think of? What happens here?
Point contact.
Point. So there is a possibility that the two surfaces touch each other at a point or points. Any other? One more.
So they will coincide.
Exactly. They may overlap, right? So I may have one surface going like this and another surface, touching it like that, right? So this one goes like this and this one is coming out in that direction and they touch each other over this much portion, right? So the intersection can be a surface itself, right? So those are the possibilities of intersection. And so it would imply then that any solution that you get must cover all these possibilities, right? And that's the first disappointment that we have with the CAD systems or the intersection routines in the CAD systems is that no CAD system can get you these two results. The only results that you can solve for using the surface-surface intersection problem is either the curves or the fact that they don't intersect. You cannot make out if they are touching each other at points. You cannot make out if they overlap. That has to be done interactively by the user. So as you can see, that's a huge, bad news for us. Yeah.
So is that why? So when I use fusion, I noticed that when one point touches a surface, it shows error. So is that the same reason?
Yes, maybe. I mean, I can't imagine that fusion is able to detect that a point is touching it. but you cannot carry that into your model at all. That is not allowed because it will cause problems everywhere. Okay. I would need to see that. I'm impressed that if Fusion is able to catch that, because that is involving some computation, right? Touching is a very difficult thing to compute. And so I would like to see it to comment, but nevertheless, it's a problem. So only these two possibilities can be addressed in your system. Now let's look at a quick overview of what the process looks like. Right. So I'm going to draw one surface. Let's say, this is one surface, and let's say another surface looks like that. Okay, so those are the two surfaces. So clearly, there is some intersection right here. So I'm going to use a different color to mark the curve of intersection. Okay. So let's say that this is the UV curve, and let's say this is surface, and let's say this is the TW surface. Okay. So how does it work? So most approaches will do the following, which is that they will discretize one of the surfaces, in this case, let's say the orange surface, into grid lines. So these are all constant U curves. And constant V lines. I'm fudging these lines a little bit, but these are all constant U lines and V lines. So here, these are constant V, and this is constant U. Right? So if I go back to my original equation, this will look like this. U star V equals S2 TW. Right? So I have a curve and a surface, and I can find the intersection of that. And I'm going to, let's say, circle it here. I get this intersection point, I get another intersection point, one intersection point here, one intersection point here, and okay, those are the intersection points. Because the result of this is a point, right? When I intersect a curve with a line, I will get, what will I get? I'll get values of V star, T star, and W star as a solution. Right? So this U star and V star will give me the point on this surface, and then T star, W star on this surface will give me the same point, and therefore that's my point of intersection. The red blue dots are my point of intersection. And that's the second problem. Do you see the problem now? While we said that we are going to solve, and this is what you do in surface intersection. Okay, you basically define a grid of points, constant parameter curves, and do intersection with the other surface. And you can do it either way, meaning I can discretize this and intersect with this surface. Then you can even discretize this and do it with that surface so that you get many more points on this if you want. But nevertheless, at the end of the day, all you have is that. Right? I hope you see that. That while we started out by saying that my intersection between two surfaces is a curve or a set of curves, right? But all I get from my computation are only a set of points. And that's the second problem. How do I go from set of points to a curve now? So I finish all this gridding and do that many intersection equations, solve them, get points. How do I get now a curve of intersection from that? You have done this. You are now given points that lie on a curve, right? The blue dots are points that lie on the curve that you want. And you want to find the expression for the curve. What do? right? That will give you a curve. Correct? So I solve, I get a grid of curves on one surface, U star constant or V star constant, doesn't matter, right? And I get a bunch of points on the curve of intersection. And I fit a curve through that and I'll get my intersection curve. Do you think that's a good solution? You should be happy with the solution? Yes?
It won't be exact.
Exactly. So that is one problem right there, you said. Actually speaking, it can be exact if I calculate R points from this process and I set my control point for this also to be M, then I can get exact. Right? That's what we found. That when my number of control points for the curve is same as the number of input points on the curve, I'll get an exact solution. But when you're doing intersection, you will do 100 curves in one direction and 100 curves in the other direction, which means potentially you can get 150 to 160 points. You're not going to have a control polygon of 150 points. So typically in all these cases, you will find that R is not as great as in scanning, but definitely it is greater. And therefore, what is the implication of that? The curve that you get is not exact. The points are exact, but now you have no guarantee that all those points are on your curve or not. And that's the third problem. That you actually will never get a clean, exact solution for the surface intersection. Okay, and this causes a lot of problems. What I'll do is in the next class, I will give you illustrate this with an example and show how we can fix this problem, but even that fix is not exact. And then we will wait for solid modeling to start to see where these things begin to hurt us. Okay, I'm going to stop here. Let me know if you have any quick questions now. I'll answer them. Otherwise, we'll pick it up on Monday. Any questions? Okay, if there are no questions, then I have just one other thing to say, which is that I thought we'll start the labs from next week, but I just saw some announcement that next Wednesday is declared a holiday. So we will try and start it from the week following that. We will have, I think, 6 weeks with us, and hopefully we can get some training and 6 exercises done. That's my plan. I still don't have the resources for that yet, but I hope that in the next 1 week, I will straighten that out so that you can start your lab sessions from the week following next. Okay. Meanwhile, I would only urge you to sort of send us a mail saying what tools you have access to so that we can plan accordingly. Right. If any help is required for you, then we can do that. So please let me know by either a message here or an email to my account. What tool do you have access to CAD tool? Okay. We want you to be able to design a curve, a surface, and a solid. Broadly, that's the expectation, right? So you should tell me what tool you have access to, and then we will figure out how we can do the training around that. Okay. Yeah. Go ahead.
So the students have access to Fusion 360.
Fusion 360.
Yes.
Okay. But not SolidWorks, is it?
I have studied, but I don't know about it.
Okay. No. I'm talking about access, not knowing. I'm not saying that you know, but do you have access to it?
It's pirated.
Oh, okay. Don't use it. Are there any undergraduates here in the class right now? 9 students. I can't believe there are any undergraduates here. So we need to ask them. So, okay, fine. I will send out a note on this Teams page itself and sort it out. I mean, Fusion 360 is okay, except that I don't know. In the past, we never did any formal training on Fusion 360. So I need to find out who can give an introduction so that everybody comes to speed to at least some level so that you can start doing your exercises. So I'll figure this out. Okay.
Yes, sir.
Thanks. Yes, yeah. We'll see you folks next week, Monday.
Thank you, sir.
Thank you.
Bye.
Bye. Yeah.
Thank you, sir.
Bye.